Hey, welcome back. Today we're going to be talking about what an electric field is. In fact, we'll talk about what fields are in general in physics and how you draw electric field lines with examples. So let's go ahead and get to it. So first of all, we've talked about charge and how charge is a fundamental property of matter. Some pieces of matter like protons are positively charged, some pieces are negatively charged like electrons. And we've also talked about the electric force. That would be a force, in this case of attraction. You've got extra electrons being rubbed against the balloon and collected by the balloon, and electrons missing from the hair. So as a result, the hair is positively charged, the balloon is negatively charged, and they are going to attract each other. We can also think of this as a field. So let's talk about what a field is. And for a moment, let's think about the Earth, and I'm going to talk about a field in general. So let's imagine that we have an object right around here, and that object has some mass, like some sort of satellite that's moving around the Earth. My question is, what would be the direction of the force on that satellite due to gravity from the Earth? What do you think? Well, it's going to be to the right? So how about if the satellite was up here, what would be the direction of the force on the satellite from the Earth itself? Well, that would be going down. How about if we had the satellite over here? What would be the direction of the force? That would be to the left. And if the satellite was in the bottom, below, down below here, what would be the direction of the force? It would be up, of course. So in general, what's happening is anywhere in this three-dimensional space, we can think of it as 2 dimensions or 3 dimensions, or just sidestep it and just say space. Anywhere in this space around the Earth, it turns out that anything with a key property, in this case the key property is mass for gravitational fields. If something has mass and it ends up in this one of these locations around the Earth, then it will immediately experience a force. And that is what we mean in general by a field. A field is an area of space where if you placed an object with a certain property, it would experience a force. And specifically in the image in the upper right, we're talking about a gravitational field, and the key property here is mass. If something has mass, it'll experience a force pointing towards the center of the Earth. Alright, well, let's use those ideas and apply them to an analogy for an electric field. So let's imagine we have a charged object right here, Q. This could be like representing by a strand of hair or something. And let's imagine we have a small positive test charge. Now I want you to remember, what happens to positive charges? What do they tend to do to each other? Well, they tend to repel each other. So if I were to place a small positive test charge right here, then they would apply a force on each other, and on this positive test charge right here, it would experience a force to the left. Well, what if we placed a small positive test charge right here above the larger charge, capital Q? What do you think would happen? It would experience a force going up. How about if the object was to the right? What would be the direction of the force on that object? Well, it would be to the right, and below it would experience a force going down. So in a similar way to what we talked about, although instead of pointing in previously, now they're all pointing out, so somewhat similar way, we can say that there is a field around a charged object with significant charge. It will have a field around it. It's not a gravitational field, it's an electric field. The key property in this case is charge. So if you place an object with some charge, it will either be attracted or repelled immediately. It will experience a force in that area of space. And it's really crucial, though, that we are saying it is a small positive test charge that's going to be used to determine the direction of the electric field lines and the direction of the electric field in general. Okay, and so I'm going to talk you through some examples of how to draw these electric field lines given these charges, these overall charges that you can see on the screen. It would help if you pause and grab a sheet of paper and try to do this on your own before you see the answers. You'll learn more if you try first and then see the answers. And so if you want to pause after each one, go for it. So first of all, on the charge on the left, for example A, any of the electric field lines that begin on the surface, remember they're going to move away from positively charged objects, because if we imagine we have a small positive test charge, like say right here, then what that means is it would experience a force down in this electric field that it would find itself in, because the overall plus Q on the left side is going to be applying a repulsive force to a small positive test charge, right? So it is easier to deal with the electric field lines that are not the ones that are interacting. As they start to interact, they get a little bit more difficult to deal with because remember, they repel each other. In other words, electric field lines don't cross, and what happens is you end up with something maybe like this, where the force on a small positive test charge in between these objects, they would essentially repel each other. So I'm going to pause now. I want you to anticipate what you would see for example B. We're going to start out the problem very similar to what we had just done over here. These are your electric field lines going out. Now remember, for a negative charge, these electric field lines are going to be pointing inwards over here for this negative Q because they would attract a small positive test charge. So we're still going to have something like this, but in this case, in between, we're going to have the electric field lines get attracted over here. I can make that a little bit prettier, but I think you get the idea here. These are your field lines would look something like this. All right, let's try C. So if you want to pause right now and draw as best you can and see how it goes, go for it. Okay, so for C, we can draw the electric field lines. Remember, they're going to be moving out from a overall positive charge. So, and then over here is going to draw in these electric field lines that are coming out of Q, positive Q, I should say. Now, the real kicker, though, is remember, I'm going to try to make this a little more clear, but the real kicker is this is a negative 2Q. So I want you to think about what's happening here. First of all, we still have electric field lines going in like this to the negative Q, but because there's twice the amount of charge, we should actually draw twice the amount of electric field lines coming in. So I'm going to draw more arrows, try to draw a doubling of the arrows, so to speak, going into negative 2Q as opposed to leaving positive Q. All right, pause for a moment and attempt example D if you choose. All right, so we're going to start with this. Remember, these are probably the easiest to deal with, the ones that are pointing away from everything else. Because these are positively charged objects, it's easy to anticipate what would happen here. This is where it gets a little bit more dicey. So remember, these will repel each other and they're never going to cross. So you might have something like this. You would have like one maybe coming out here and one maybe coming in, so to speak, over here. Remember, we're going to have other electric field lines that'll come down. So I could draw one like this, here, here. We could have another one coming in like this, and one coming out. Let's see, maybe we could make this one loop in, and maybe we could make this one loop in as well to kind of show the effects of this. Some of these are actually easier to run in a simulation to see exactly what would happen, but this is the general idea of what you would expect to see for a set like this that has 3 charges. All right, how about this last example? So example E, pause if you choose right now and think about what's going to happen. All right, well, what's going to happen is you have what's called a uniform electric field. There's a reason why I'm bringing this up. This actually is more important than you may realize. This is what happens for capacitors, which you may or may not have gotten to at this point of the year. You do have some curving around a little bit like this, but essentially in between the 2 plates here, you're going to have a uniform electric field in this section aside from the very edges. All right, so let's summarize what's going on with the electric field lines and what we've learned from the examples. First of all, electric field lines never cross. They start on a positively charged object or infinity. We represent infinity by the edge of the page or the section of the page that we're working with. Electric field lines end on a negatively charged object or infinity. They're closer together where the nearby charge is greater. They're proportional in number to the magnitude of the charge. So if you're dealing with like 1 charge of Q, 1 charge of 2Q, then the 2Q charge should technically have twice the number of electric field lines. Also, the electric field lines are perpendicular to the surface of the charge. So hopefully this has been helpful. I've gone over lessons for an entire year of physics and most of the concepts for an AP Physics C mechanics class. If you have any questions or comments down below, please let me know, and I hope you all have a great day. Take care.